we'll have Martin Mikulski giving us a talk called Can the Semantic Account of Computation Be Trivial?
Thank you for having me. It's great to be in Jerusalem again. And, the questions, there's the Bataille's law about journalism that says that questions in the headlines, they should be always answered with no. But my friends actually checked whether the law applies to academic journals. And the answer is no. So my answer, of course, I could say the job of a philosopher is to ask questions rather than to supply answers. And I will be mostly asking the question, but I think the answer is a tentative yes. It can, and it very easily be trivialized. So that's my idea. So the first thing is that I'll go through the semantic view, then I will have the worry and two basic strategies of responding to that. There might be more strategies to work with. And then that's it. So I will be talking mostly about Oron's version of the semantic view. That's the semantic view that I want to focus on, because it's actually the most trivializable of all, which is surprising, but you'll see why I think so. So the semantic view, which usually is simply considered to say that semantic properties are an essential aspect of the nature of physical computing systems. That's shared by many proponents of this view. And the primary motivation for that would be to classify computing systems against non-computing physical systems. Like planetary systems do not compute according to Jerry Fodor because they do not represent their orbits. It's a very elegant solution to pan-computationalist worries. So it's a nice thing. So it's a primary motivation for many. And that was also defended in a new version by Oron as well. So here's my trivialization worry. So it was defended by making it a little bit more nuanced. The problem with Fodor's view is that it relies on the notion of original contents, which in Fodor is extremely difficult to understand because it is supposed to be, first of all, somehow innate, but still original. But how would you have innate, what was that? Whatever, a combustion engine as the innate concept having any meaning? Or a computer in Aristotle's mind as innate. That seems paradoxical. I don't think it is as paradoxical as it sounds, but still, he had lots of problems with this. And for our purposes, the worry is that it's not so easy to build a machine that has original contents. It's not obvious that all machines have original contents. And there are people who would argue against it by saying that the symbol grounding problem is a genuine problem. That's why we have to be more nuanced, and the nuance comes from the idea that it might be either original or derived contents. Here's the worry. If you go for derived contents, it's easily trivializable. So let me just remind you how it went. So the Turtle and Putnam would claim that computation is not objective, and they would pick on the one-to-one mapping, the simple mapping views, just to say it leads to catastrophic pan-computationalism that implies that almost everything implements all algorithms at the same time. Almost, because maybe a geometrical point does not. But for Putnam, it was, of course, closed physical system. So it's an idealization. For Searle, it was sufficiently large, not clear what it means, but it was meant to say most physical systems would implement all algorithms at the same time, which is not a nice thing, because that would mean that if I provide somebody with an information that this computes one algorithm, that it executes one algorithm, that does not provide any information because it does not exclude the possibility that it computes another one. So that's the word. So the alternatives seek to avoid the catastrophic interpretationalism that the causal account does that by simply saying that you cannot map algorithms or computation to physical systems freely. You have to follow the causation. Mechanistic account is even more constrained version of the causal account. And the semantic account promises to do the same by saying, it's the representations that do it. But it seems to do the work for original contents, but I'm not sure if it does if you have the derived contents. So here's my tentative claim that the semantic view in this liberal version can be trivialized. So if you don't want to presuppose a substantial notion of contents, which is seems like a reasonable assumption, then you have to do something to make the semantic view more liberal. And there are people who also defended anti-representationalism, meaning no original contents in computing machines, like Joe Dukers, who's no longer doing philosophy of computation, but his views do not seem to be contradictory as such, so it doesn't seem to involve an internal inconsistency or whatever. You might deny the existence of representations and still say that there is computation. So it seems that it would be a little bit too strong to say things that Fodor would say or similar views. So the pluralistic view is featured in Chagrier, that representations may be extrinsic, so they might be merely ascribed by observers, or they might be intrinsic. But if they may be extrinsic, then they might be observers as evil as John Searle, or even more evil, which is difficult to imagine, and ascribe representations. So Searle could simply come here and say, look at this wall, I will be now ascribing representations any way I want. What stops me? I want that. It's my intentions that ascribe derived contents after all. And here's my intention. My intention is to ascribe representations that would be featured in iPad here. Here's an iPad. We know that it's a weird idea. We know that nobody would buy this wall as an iPad, but that makes it a proof by contradiction or indirect proof of the incorrectness of the semantic view, basically, for me. So it's a word. So the core issue is that the liberal semantic view does not presuppose original or intrinsic intentionality. But then, if it does not, then you can do mirror ascriptions, and these mirror ascriptions can be from Searle's ascriptions to Egan's mathematical contents, whatever you wish. Because it was supposed to be liberal, but it is so liberal that it unfortunately opens the door to the same strategy that Searle would be using. So, although it seemed less open to objections, I think that it actually opens the door to the major objection. But I think there are at least two responses to that, and I want to discuss them today. So the first response, here's what Midjourney thinks John Searle looks like when he's laughing in a caricature version. The first thing is to stress one thing which is featured in Traceri's book, namely the distinction between individuation and implementation. So the semantic view is not supposed to be a theory of implementation, of physical implementation of computation, but it's a theory of individuation. It would be more useful to distinguish various computing systems which might even share the same physical implementation. So there might be, that makes a virtue of something that many would consider a vice, namely that there would be logical gates interpreted in two ways. That is the individuation idea. You can individuate the same gate as or, on, or and. But it's not telling you anything about implementation. So it needs to be enriched with the implementation. So that would be one way of saying, well, you are forgetting that the view is not supposed to answer the worry directly. So maybe I'm missing the mark, and that is possible. But what bugs me is that in the chapter in the book in which the semantic view is introduced, Oran discusses limited fun computationalism as a possible objection. So if limited fun computationalism is an objection to discuss, then why not unlimited as well? And he responds it without relying on a heavy notion of implementation, and says that limited notion of fun computationalism implies that every process happens in virtue of information, because that is one version of limited fun computationalism that could be pressed against the semantic view. That limited version would be, for example, that all causation implies semantic information, which is something that John Collier would claim. And then if that's the case, then all causal processes are also could be, because they carry contents, they could be ascribed computational properties. But what Oran says, that does not happen in virtue of information. I'm not sure if it really stops Collier's view, because if causation is transfer of information, then it happens in virtue of information, nothing else, because causation is the transfer of information. So you would have to show that there's someone notion of causation which was referred in terms of information by Collier is totally inadmissible. To do that, we would have to spend some more time. I think I find ways to defend Collier's view in spite of the objection. So I don't think it really works, but still it shows one strategy of replying to fun computationalism by relying on the notion of not relying on the notion of implementation. So the worry in that might be raised against this strategy of responding to trivialization argument is that, well, it's not the semantic view itself that dispels the worry, it's the things that you assume in addition to it. So there is a very nice small children's poem in fairy tale in Polish that tells you a story how you can make a soup from a nail. Well, basically you add water, then you add some butter, then you cook some vegetables, and then you add some groats, and then you have a beautiful soup. But the role of the nail is unknown, and I think that would mean that the semantic view is like the nail here. It's a nice ornament, but it does not really do the spelling of the trivialization thing. And that was, let me stress again, the primary motivation for it, to distinguish computing from non-computing systems. If that does not really work, it's not a soup from a nail, so it does not seem to work here. And let me just stress that in my simplistic version of the argument against the semantic view, I did not require any semantic information. So I don't have to say that it happens in virtue of information. It's a computation in virtue of your ascription. Ascription of representations, of derived representations. So it's in virtue of the intentions of this nice privileged male human being. Right? So I don't think it can be easily dispelled unless you get away with the notion of derived contents, which is difficult. So that strategy does not seem to be effective. So let me just focus on another one that seems to do the work to some extent. So it's we'll be going to a more happy note. The happy note is that first of all, well, several ideas. First one idea would be, well, just get rid of the derived contents, go for semantic information. But I think it's that this strategy would be hopeless. So the second strategy is to constrain semantic ascriptions somehow. But requiring semantic information in constraining ascriptions is hopeless, because even if you don't believe that Collier's account of causation is correct, Dresky definitely would show that the semantic information can be ascribed to things that do not seem to be computational, because they are probabilistically related. So it's sufficient to show that two things are nomologically related to show that one carries information about the other, and not some of them would be planetary systems which do not seem to compute. So that would outstrip the bounds of the computational process. So that would be too much. So I don't think that strategy would work. Another strategy of constraining would seem to be more helpful, focus on simplicity. And that actually has been tried before by numerous authors. My friend Paweł Grabarczyk has actually published a paper. I don't know why he did that in Polish, but he did that in Polish in 2013. So it was left to obscurity. But then he went to game studies, so maybe he doesn't really care about that anymore. But then Milhouse rediscovered the same argument in a different version, and I'm slightly in a simpler version. Basically, that says that computational ascription should not violate simplicity considerations. So if your ascription, so your strategy of ascribing is more complex in some technical sense than the physical system that you're ascribing this to, or as complex, then you would get a problem. And of course, Milhouse as Grabarczyk as well, they rely on the notions of Kolmogorov complexity. So it's the algorithmic theory of information in which you basically can operationalize the complexity of information by relying on the notion of general compression. So if you zip information about the physical system, you zip information about your ascriptions, and you see which one is longer. If your strategy of ascription is longer, then sorry, goodbye, that's the end of it. But you are left with ascriptions which are equally simple. So it works to some extent, but it's not catastrophic. So not all our algorithms, but all in the same set, in the same class of complexity, or simpler. So this one could be ascribed, lots of atoms to be a gate. Very simple system, very simple model. So it works to some extent. It's not all, it's not catastrophic, but still leaves open the question, how would we get rid of these non-genuine ascriptions? And remember, the non-genuine ascriptions are difficult to get rid of because they are based on intentions of John Searle, which are known to be evil. I mean, that they're intentionally bad. And how do we stop it? But people can do that. I mean, you can use this to mean something. we make a convention and it seems to work. So it's difficult to say how we stop that. So I think what is needed here, we should require the notion of implementation. So there is no way around this. And if that's needed, then it makes the semantic view not so bad, but it makes it incomplete. And moreover, one critical issue in algorithmic information theory, if you want to compare complexities, is that you can compare complexities only if you have one canonical notation or canonical description or formalization. So you cannot compare against two different schemes of description because these might have some baseline complexity in themselves. So you have to go to the same formalism. That might be a Turing machine, that may be anything that generates the string that you want. So you have to agree on that. But if you don't agree on that, in some way, you cannot. So to do that, you probably need to agree on what is the bottom level, what is the physical level that you start with. So how would you know how complex this wall is? Difficult to say, depends on our theoretical perspectives. If you're a philosopher, it's a very simple thing. But if you're interested in forensic analysis, maybe you're interested in many fingerprints here, or weird substances left by fingers. Were the people smoking pot the day before they were speaking here? Maybe that's what you're interested in. Then it's much more complex because many more states would be required. So we need something like this, and that means that we need some notion. We need to rely on this, and the semantic view does not seem to supply that. So that would have to be somehow accompanied with the addition here. So what seems to be implied here? Well, what seems to be my analysis, which may be a little bit too hasty, seems to suggest that you need a substantial account of implementation, because without it, even those simplicity considerations, and you could probably think that some other considerations could be in place, like beauty, aesthetic properties, or other virtues that you might require from your, or generalizability or something like that, that they would not be ad hoc from one system to another. Maybe something like that would be required, but I don't think they would leave that they would constrain the things sufficiently. But the only reason to defend the view actually seems to have been that the computation is not determined by implementation. And let me just stress one thing that seems to be a core disagreement between mechanistic views and Oron's view. Maybe the mechanistic view insists that we individuate mechanisms by their phenomena. So we have an obligation to look at the phenomena that we are supposed to explain. So we need to individuate, we must individuate mechanisms by looking at the kind of mechanism. And maybe some of them are semantic mechanisms, maybe some are not. So it might depend on the kind of mechanism. And elsewhere, I defended, unfortunately, only by talking, a view that actually in different contexts, we might have somewhat different notions of what we mean by computational phenomena. So some disciplines might be interested in semantic properties, but if you're a computer engineer, you might not be really interested in what these machines can do. You want them not to heat up, to save space. That would be the properties that you're interested in, but that's your phenomenon. That the one that does not explode, does not they give up the smoke and anything like that, which would happen in the past, of course. So. The mechanistic view, in other words, already includes the distinction, but includes the distinction in a package, along with the notion of implementation. So we already embrace some part of the semantic view for some phenomena at least. So why would we go for the semantic view itself if it's weaker? So you could raise, of course, the considerations that gather us here, that there's indeterminacy of computation. But if you believe, as some of us might be tempted to believe, that it's just like theoretical underdetermination, just so happens that people focus on computation, but it's everywhere. So there is no reason to worry so much about computation. It's not the data that tells you that you should describe it this way or another. You always have a possibility to describe experimental data in different ways. So that does not seem to be very worrisome to a mechanist. So basically, what seems to be implied is that the semantic view is just a gloss over a substantial notion of implementation that does the real work. And there are cheaper options. And on that happy note, I thank you for listening. Yeah. I think Oron wants to speak first, and I think that is all.
Yeah, well, so few comments. First, about the semantic view, I think it is true that under the semantic view, you could view in principle everything, including the wall, as a computing, or the stomach or something like this. But I think that there is an important difference between you could and what happened as a matter of fact. As a matter of fact, we don't describe content to walls and stomachs, etc. So they don't compute. You could do all sorts of things and look at them, and then you could view those systems as computing. But as long as you don't, the systems don't compute. A second comment is that in this respect, there is no difference between the mechanistic view and the semantic view, because on the semantic view, you supplement the idea of some mapping or implementation with teleology. And again, if a designer or user could really engage with the stomach or the wall or things like this, then under this, and then the system would have the function to implement or to manipulate in a medium independent fashion, whatever, then the system also would compute. So there is no difference between the semantic and the mechanistic view in this respect. The stomach and the wall could, in principle, I mean, no one really seriously thinks that to do something like this, but in principle, there is no difference between so this is the second comment. The third comment is that you talked about observer relativity. So here also there is no real difference between the semantic view and the mechanistic view. In the mechanistic view, people do the distinction between the observer versus designer / user. And the teleology of laptops, I mean, and things like this is connected with designer and user. The semantic view, it's the same. No one, it's not like an observer. It's not that the scientist assign to the wall the content. Is whether this, the question is whether the designer or user assign the content. So again, no difference between the mechanistic and the semantic view in this respect. Now, about implementation and triviality. So I completely agree with you that the implementation, a good theory of implementation and a non-semantic theory of implementation, like Sharmas, do the job, and then we get rid of unlimited time computation. I mean, this is so I grant this, and for in my semantic view, I think that computation, one condition on computation is a serious theory of implementation. But the question is what else is needed? And this is the question that is raised both by the mechanistic and the semantic view. Because again, a stomach implements some formalism in Chalmers's sense, but it does not compute. It does not compute, it could compute, but it does not. So, both according to the semantic and the mechanistic view. So in both, so you need some condition. So the semantic view says, okay, the condition is representation. The semantic, the mechanistic view says it's teleology. So this is really the difference. So I mean, so you are right in saying that we don't need to employ the semantic view in order to get rid of triviality. We can do this with a theory of implementation. I completely agree with this, but what I'm saying is that a good theory of implementation, like Chalmers said, is not enough to define computation. You need something more. This is also acknowledged by the mechanistic view. And here we just differ what else is needed, whether it's the semantic representation or teleological function. That's what it is. Lastly, I also agree with you that the semantic view should better come. You need some more serious, or let's say more constraint on the semantic interpretation. And I do this in the last chapter of my book, that I say that, yeah, not every system that represents also computes. So this is why I added this input-output modeling constraint that I think is doing at least some of the job, I don't know if all of the job. So yeah, so these are my basic comments.
Thank you for that. And one, I'll try to be brief because I saw other people also raising hands. You're saying that we don't, in fact, perform these descriptions, but there are some contentious cases, like in the reservoir computing, in which there's a genuine disagreement whether this system, like a pile of water which is systematically perturbed by a robot hand, is a liquid state machine or just a pile of water. And there is a genuine liquid state machine. If you Google it, it's a very funny thing. It has a movie to it. So sometimes people have a genuine question whether it does or not. And there are lots of people like Adamatsky and so on who have genuine hypotheses that mushrooms do it, that other systems do it. So in fact, they do ascribe things to other people, to things that other people would find quite intuitively non-computing. So because we know that they do that in serious publications, they might even in the lab entertain even wilder hypotheses. And so I'm not so sure that we can say so easily that we don't in fact do that. Well, some of us don't, some of us do. So I'm not so sure that it's not that it comes so freely. But the distinction here, it's not just the teleology. The mechanistic view requires, by definition, that the ascription follows the causal structure, and it maps onto the causal structure. You could have it in like 3M constraint dependent by Kaplan and Craver, which simply says that it should the computation model should latch on one-to-one. And then it seems that it is more restricting the descriptions than the semantic view, because in the semantic view, you could actually do something that does not track causation at all. If you had some other account of implementation, Because that seems to come from the theory of implementation. And that's the distinction. So my worry was with the class of things that are not excluded by the simplicity. So the class of weird ascriptions, that some of them seem to be really weird, and that there is no downstream use or anything like that. Maybe with input-output constraints, you could do that, but the problem is with input-output constraints is that there are inputless machines, and you might think that for some computations the output is sometimes very trivial, and some people have defended that in print, like Aaron Sloman would say that all interacting machines have trivial outputs because we don't care whether they finish. They should not. We want to interact with them in an infinite loop. So there should be no output. And for the ATM, it's a simple machine. We don't find output in a very interesting. If it outputs is one by saying, well, the Windows version is now update, please update me. It's not something that we're waiting for. We are waiting for the individual steps to finish, to ask us to enter your PIN and so on. So I think this is that then does not allow us to take a view that it's just input and outputs going that do the work. So that would be my.
So if I may, really quick points. First, I think that I don't think that computers, maybe brains, are natural kinds of or natural, but I don't think that in general computation is a natural kind. So in the first example you mentioned, yes, so some people might describe the system as computing, while others do not, which is fine. I also think that the causal structure is important, but it is important for the question of computational equivalence, where the two systems are not for computing itself. And with the input and output, I also agree with you that I'm saying, okay, I'm assuming for simplicity input and output, but I mean, the main example I discussed, like attractor neural network, there are no input and output in any obvious ways. That's, thank you.
Andre? Yeah, thanks as well. So I'm interested in the kind of assumption that you make to actually have this like sort of equal Searle interpreter worry off the ground. And it looked like the assumption that you're using was just like, look, if someone can cook up a DBS sort of interpretation, that suffices to give us extrinsic conditions. But I guess I don't know. That seems like kind of optional, and sort of understanding that there's more sort of robust view of what it takes to ascribe sort of extrinsic representations to something. And just to sort of put some meat on that, I mean, when I think about like giving a deviant interpretation of like a piece of art, my language arts class, it's not enough that I just say, here's the interpretation. I have to kind of tell a story that aligns with the relevant sort of practice, in this case, the relevant sort of art practice. I have to get uptake by like community users. And so there's a little more to, you might think there's a little more to than just, as you're saying, oh, here's the interpretation. So I don't know what you think of that, but it seems like sort of there's room there to understand to diversity a little more.
I don't think it's a helpful strategy because especially in art criticism, sometimes you're not interested in any constraints whatsoever. You're interested in how people react to this, and how they react might be actually a function of how you interpret this yourself. So there might be very limited agreement on what the art does. So there are basically several views on how you interpret works of art, including literary work, and some views are related to the structure of the work, and some are related to the response of the consumer. And in some attempts, it's the affective response, which is the most important one. And then the affective response of John Searle is just to describe the computation everywhere. Why? And he finds it fruitful, and there's a lot of people who find it fruitful, and they really find really pulled by this. They feel emotionally attached to that interpretation, that's enough in art. They're emotionally attached to the idea that there are no computers. There are lots of people like this. They would say there's a computer metaphor, there are no computers. It's not a matter of fact, but that there's a computer. Why they pay money for computers, it's beyond me. I wouldn't buy a metaphor, but they seem to be ready to buy metaphors. So maybe it's just like art. So I would be very careful in this because the actual practices are very relaxed in this camp. And there is also a recipe, strict recipe that Putnam gives us. I mean, it's a proof. And that proof is generalizable to the systems with input, and it all does not even require a clock. It requires just a dense source of signals, and it does not really. It cannot be really disposed with counterfactuals, because you can have simply more complex things because there is a recipe, it's an algorithm for expressions. So it's a very, very, very mechanistic, I mean, in the Turing sense, like there is a recipe for producing these descriptions, divine descriptions. If there is a recipe that they do not seem to be totally, deviant, because there is a strategy that Putnam uses, and nobody has. I mean, the proof seems to be correct in the representation in reality. So I think it can be used to produce deviant encodings or something like that, or anything. So I'm not sure whether that would suffice for this reason.
Sure, so that was just, the art thing was just sort of like an example. I guess sort of, the deeper question is like, why think that merely ascribing some computational interpretation is enough to, well, why think that extrinsic interpretation or extrinsic representation is so easy to tell? Like, couldn't we have a robust view of what that consists of? And that seems like something part of this time.
Because it seems to latch on our semiotic practices. We can use a flower pot to say that this room that there's police already in this room, do not come upstairs. We could use a lot of things as signs, which is some by convention. We can decide what to do, and there are lots of ways, and some of which seem to violate this simplicity consideration. So you can use a very complex physical thing to say a very simple thing. So it's I think that we can simply concoct certain encodings that could be, a very complex signal in which just one bit is relevant, but the physical thing is very, very complex, and we do that. That's the steganography is a practice. You send a very complex signal. People look at the signal, they think there's something else, but actually there's just one little hidden thing which is in the open, but just because of the complexity of the thing, we don't see that. Only the person who is the intended receiver can decode that. So I'm not sure whether we can do that in principle, exclude that. So that's why I was much more skeptical of this.
Yeah, thanks. So part of, maybe I misunderstood, but part of the argument is that the semantic view has no space for original content.
No, that was not part of my.
Okay.
I said it's like the disjunction. It has to be representation which can be original or derived or ascribed. But I did not focus on the original.
It's XOR, it's or
No, well, probably you can ascribe contents to things that have original contents. And I do that at this point. I ascribe contents to you, and you have original contents, but my ascriptions are probably in some ways inaccurate.
Yeah, okay. So
Maybe
I thought it was
yours
one of the
are
arguments.
as well. But
I would say that I can see a path with the semantic views to describe original content or to accept original content.
yeah,
It's just not.
I totally agree. With original contents, it's easier. I mean, but the worry is that not all computers have original contents.
That's fine.
Yes.
That's
So for
Just
that
that-
class, we need something else.
Okay, so that was, that's what was your.
Yeah.
Okay, fine. So then then I have not much to add. Okay, about the original content, but I think that's an interesting question for this. And I think there's something to be said about it, but maybe that's not the topic right now.
I just, I mean, you put, I think, I mean, some of your remarks, they were not central, but there were some comments about the simplicity view and so on, and I just don't see why you, I mean, why to put the emphasis on this view in particular, because, I mean, a physical system has many properties. This is what we were told by physics. So if we can construct a mapping between the various physical properties and computational states, that's all we need to do. Whether the physical evolution of these properties is simple or complex or whatever, I think is sort of an epistemic issue, so it's not really because it's not going to cut the question, to settle the question about whether the system compute, but maybe the physical evolution is very complex. So, and this is one comment, and the other comment I think is what's nice about the semantic view, I think, is that if you were thinking in this way, that semantic content can be attached to various physical properties. And then this view, the semantic can be constructed or thought about in a way which is compatible with the physicalist view of computation.
Thanks for that. Actually, I'm skeptical of reliance on simplicity for very similar reasons. I would even be entertaining a hypothesis that there's at least potentially infinite number of properties that you can find in a physical system.
Yes.
And because I'm realist about physical things, so I think that you can go more granular and more granular depending on, especially if you think that relational properties count, and they have to count because otherwise you don't have fields. You have to. So I'm not, I mean, I think one of the worst things that happened in philosophy of physics was Ernst Mach, whose book I translated, and since then I deeply hate, because that's the worst idea that you could have, that simplicity answers all the questions. It does not answer almost no questions. It answers almost no questions. But just to defend Milhaus and Grabarczyk, their idea was a little bit less nonsensical. The idea was that if you have a physical model of a system, and then you have a semantic model of that system, which is computational, you have two models, and then you can compare the complexity of both. And if the complexity of one outstrips the complexity of another, especially if the computational seems to outstrip your physical model, it seems that you're ascribing things which do not seem to latch on anything that you could find in the physical world. So I understand why they would say that, because that seems to basically explain, and they go on to explain that in some of their remarks, why we don't buy an old computer and ascribe Mac OS system to that computer, because we have to do the work. So there's a physical work done required to do the ascription. So there is a huge physical amount of work which is required to do these ascriptions, which are impossible available, but they are still physical processes which would outstrip the complexity of the old computer. So I think that's why they stress on this. But to do that, they need to have pick the basic physical descriptions that we start with. Without it, it's just you have the infinities which are undefined, and it's the comparisons of simplicity are wrong. But simplicity is just one example of theoretical virtue you could have for beauty, you could go for systematicity. So there are various ways you could try to go, and which are not simply accuracy. So I think that was the idea, to have constraints which are not simply this, simply not truth, because we contend whether it's true or not, but let's use other constraints to remove some of that. So that was, I think, the motivation. That's why I was talking about that. And I think in some ways we use, in some limited sense, those simplicity considerations to pick the real patterns from nervous systems. In the signal, we use those information theoretical considerations to see whether the entropy is there properly computed, things like that, to see whether it's noise or not. So we can do that, and we do that. So I think that was the original motivation, and that's much more formal in Milhaus and Grabatchev. So they rely on the notion of the algorithmic complexity in the full blown mathematical sense.
Yeah, one more comment. So, I mean, first, what I think you highlight very nicely, and maybe I haven't appreciated enough, is the close relationship between the mechanistic view, between the mechanism itself, right, and what is being implemented, and the teleological function that is tied to this implementation. What you say, which I think is quite right, is that in the mechanistic view, the mechanistic view makes more sense because, you know, the implemented structure and the teleological function, they go together. Whether in the semantic view, you have implementation, this is one thing, and then you have the semantic, which is another thing. You have like two separate components. This is, I think, something that you highlighted, and I think you're right about it. And this is an important point to make. I just want to emphasize again that it's not that I think that computation has nothing to do with the mechanism. I think that computation is the mechanism, right? It's just that the kind of mechanism, the architecture itself, doesn't really distinguish between computing and non-computing systems. That's my point, and I think that Gualtiero agrees with this, because he also, when he presents the problem, he says, let's now think how to distinguish between computing and non-computing mechanisms. So we have here mechanisms, and now we want to distinguish between them and to say, so it's not that I just want to emphasize that it's not that I think it's not that I deny that computation is a mechanism. Of course, it's a mechanism. Just that the fact that it's a mechanism doesn't make a difference between computing and non-computing. And the kind of mechanism it is makes a difference to computational equivalence, whether we count two computations as the same or not. So maybe just to clarify this one.
I think
You interrupt us before you answer. So I guess in a sense, what you're saying is that according to the semantic view, the mechanistic account of the mechanistic part of the story is a necessary condition for computation, but not sufficient. And then you're saying that what distinguishes the mechanistic view of the next level from the semantic view is the teleological.
No, I'm saying that what in a sense, you know, in some broad sense, every physical process, right, is a mechanism. Every physical process. Yeah, almost every. Yeah. I mean, if we, yeah,
When I think about gravitation, I mean, that's a mechanism as well.
Gravitation is the force, it's not a mechanism. But yeah, every let's say every physical. What I'm saying is, yeah, I mean, you could say computing is a physical process. It's a necessary condition to be, but yeah, this is something obvious because the whole point is to distinguish between computing and non-computing physical phenomena. Right? Well, Gerald says between computing and non-computing mechanisms. Yeah, so if you want to say that physical computation is a physical process, and this is a necessary condition for this. But I don't think that it's the same.
I think that all mechanists would simply stress the importance of phenomena that you want to explain, and of course there would be different kinds of mechanisms. So not all mechanisms that we want to talk about would turn out to be computational under the mechanistic view. They should not. So the mechanisms for digestion should not turn out to be a mechanism for computation, whereas mechanisms for finding some alien things to fight with by your immune system might be computational, because the immune system, as standardly understood by theorists of immunity, is a computational system that detects those things. So that would be basically the distinction. So how we do that, it's of course some mix of understanding of what the kind of phenomenon implies to understand it, and how we understand teleology, and how we understand causation, what are the constraints on this. So I don't want to go into details of what distinguishes my favorite notion of teleological function from Gualtiero's, because I share a very strange notion of function, which was defended by Ulrich Cross, which is totally different than anybody else's. But I think it's the best one. But I mean, it's so the idea is basically that the system should be created for doing this, basically, by either the natural selection or the engineering. It should be selected for. So the notion of selection for, but might be also selected for, the parts are selected for of the mechanism as kinds are selected for the function that they have. And I think that works pretty well for all non-divine systems, because the divine systems, where their parts where they usually are not individuated as types. But you have to be realistic about types, which is fine for me. But if you're a nominalist, well, you're doomed. But you're doomed anyway. So it's a price that you have to pay for that view. So in some ways, I think what I find good about mechanistic view is that it combines several things under one umbrella, because it's a view on explanation. So it has to have those constraints, and then that's the thing. There is something read on the chat. I'm not sure if it's a question.
We also have
Diane wants to see. Yeah.
I think the camera needs to be.
The camera doesn't show you.
Oh, okay.
Maybe it doesn't show.
we have 13 minutes for coffee also. We're already
Oh,
into
so we
the
should-
coffee.
So maybe we should go to the coffee break.
Yeah.
Let's continue
Yeah.
discussing.
So Andre Curtis-Trudel will be talking to us about computation triviality and observer relativity.
Okay, so thank you to Oran and Nir for the very kind invitation, and to you all for, should I wait?
Yeah.
Okay. And thank you to you all for being here. It's been a very stimulating conference so far, and hopefully will continue to be for the next 40 minutes at least. Okay, so this paper is about, or the paper that this talk is based on is about physical computation. And there are a couple sort of main motivations for what I'm up to. One is just to try to think about computational implementation through a sort of broadly Fregean lens in the philosophy of mathematics. What do questions about implementation and about sort of issues arising in connection with pan-computationalism look like if we
think about implementation as an instance of the application of mathematics. So that's sort of a broad, big picture motivation. And then a second motivation is to think a little more carefully about the commitments that are involved in a particular kind of reaction to pan-computationalism that we find in the literature. Now, pan-computationalism has been with us since at least the 80s. And there are two, very broadly speaking, main kinds of reactions you find in the literature, neither of which is especially enthusiastic. And the first kind of reaction is to try to reject it. And the usual way that this is carried out is by rejecting the culprit, the simple mapping account. And in broad strokes, the way you do this is by
Andrea, when she finishes, we can say, this is the end of my argument.
That's right. Yeah.
Take your time, Paula.
So thank you very much. I hope you're all convinced.
So.
So this first sort of strategy attempts to sort of block pan-computationalism, or at least especially insidious versions of pan-computationalism, by restricting the kinds of mappings that are allowed to underwrite genuine computational implementation. So you get these restricted mapping accounts. And we'll see some sort of particular examples later on, but the strategy should be familiar. And so the second sort of reaction, that's the one I'm in a way more interested in, basically accepts pan-computationalism, accepts the simple mapping account, and tries to learn to live with pan-computationalism. Now, the way that folks typically try to do this is by sliding into a kind of observer relativity about physical computation. I guess the exemplar here would be Searle, but you find it in more recent authors too. Paul Schweitzer comes to mind as maybe the most, or one of the most prominent examples. Now, this move from pan-computationalism to observer relativity typically happens pretty quickly, often in a sentence or less. And I want to sort of slow down a little bit and think about whether, even if you accept pan-computationalism, you are committed to a kind of observer relativity. And I'll say a little bit about different kinds of observer relativities that you might be committed to later on. And so ultimately what I want to do is sort of use this as an occasion to try to explore what you might think of as a kind of third way that accommodates the insights. Maybe there aren't many insights on that side, but let's say the insights of both of these kinds of response. At least I think there's sort of an interesting middle ground here that's worth exploring. And the view that kind of falls out of this does have some interesting, and you might even think attractive features that are worth thinking about. Okay, so that's sort of the big picture. Here's the game plan. I'll start just by outlining a very generic version of the triviality argument. And I want to do this because I want to extract basically a job description for computational implementation, or at least a minimal job description for what we think implementation ought to be doing for us. Principally in computer and cognitive science. I'm not going to be too worried about computationalist programs and the philosophy of mind. So that'll be the first part. The second part, I'll draw on some broadly Phrygian insights to try to reframe the challenge that's sort of raised by the triviality argument. And then I'll say something about observer relativity at the end if I have time. Okay, so let's start with these triviality arguments. I think generally speaking, you can think of these arguments as proceeding in two main steps. So the first is to argue for unlimited computationalism. That's the view that, every physical system implements every computational model simultaneously, at least for a given duration of time. And then the second step of these arguments is to move from unlimited pan-computationalism to the claim that implementation is in some sense trivial. And so the first step, you need three premises to get the to conclude unlimited pan-computationalism. So the first, at least in standard formulation, is just a simple mapping account. This says that a physical system implements a computational model just in case the two are isomorphic. So there needs to be a structure preserving mapping from the states or the state types of the physical system to the states of the computation. The next thing you need is just a little bit of model theory, which tells you that if you have two structures which have the same number of states, then there exists an isomorphism between them. I guess, nowadays this is sometimes called push through. And all it is really is a recipe for constructing isomorphisms between equinumerous or between structures which have equinumerous carrier sets. So, push through is found all over the place in Putnam's writing, and it's at least what I think is underwriting his use or underwriting his triviality argument as well. And then the third ingredient for the first step of the argument is just a cardinality assumption. This is typically an empirical claim to the effect that you have enough physical states or enough physical state types to oh, I got Zoom problems. I think I just got booted off of Zoom. No one
Do you
here.
want to connect? No, they can hear, but because you're using your Zoom, we can't let them talk because of the audio feedback. Do you have USB-C connection by any chance? Or just,
But I think it's the Zoom. I got kicked out of the meeting, so they probably can't see right now.
no, they can't.
Yeah.
But you're still connected to Wi-Fi for sure?
No, I can boot it off the Wi-Fi.
So maybe you can just use the,
No, that's fine.
you need USB-C or directly the LAN connection?
Either one works.
Go with the LAN then.
Yeah. Oh, looks like I'm back now.
Might be good to put the LAN just in case.
It's not gonna work.
Sorry?
It's not gonna work. Not gonna work. There's the bigger developed systems. Okay. Well, then that's why you need that up there.
Ah,
Are you connected to the Zoom?
no, he's,
Yes, there's the Zoom right here.
he was kicked out
So
a
if
minute
you
ago.
disconnect from our system and it just shows it on Zoom, then you'll be able to hear the other participants.
Are you okay to continue like you are now?
I'm fine to keep going
So
like
you're
this. I think it's okay.
Cool.
As long as the people on Zoom can see slides.
Let's assume they can hear us and see us.
Okay.
A good assumption.
Okay, right, so basically you need, for this cardinality assumption, you need an empirical claim to the effect that you've got enough states in your physical system such that for any sort of computation, you can find a set of physical states that are equinumerous. Now, really, this is just, so if you have all three of those things, then you get unlimited kind of computationalism. So in a way, this is just kind of an argument schema. There are different ways of filling out the details here. In particular, you can be more or less precise about this cardinality assumption. Putnam is very careful about it. Searle is very circumspect. I'm not going to worry about that here. I take this to be something like what's underwriting the first step of the triviality argument. Okay, but I think in a way, the second step is worth getting into a little bit more detail. And so, the usual charge is that unlimited pan-computationalism renders a theory of implementation trivial. And I think this actually subsumes a variety of more specific complaints about the descriptive and explanatory credentials of a theory of implementation. So the descriptive failures include, among other things, almost complete lack of empirical content. Notice that the empirical assumptions needed in the first step of the argument are extraordinarily minimal. They really only concern the cardinalities of the states of the systems involved. And so insofar as a theory of implementation has empirical content, it seems like it will concern cardinality facts, which is to say there's not much content there. Any empirical discoveries would be at best discoveries about the cardinalities of the systems in question. Again, not especially exciting stuff. You'll engender widespread predictive failure. So, you might have thought that information about what a physical system implements would have been predictively useful if you've got for example, a robot that's following, working its way through an obstacle course, you might have thought that, information about the pathfinding algorithm that it implements would have been predictably rather helpful. Now, if the robot simultaneously implements every pathfinding algorithm, some of which might chart very different paths through the course, it's hard to see how you might single out any one of these in particular as the one to use when you're trying to predict the robot's behavior. And then you get the mirror image of this sort of problem when you consider things like retrodiction. Given any pattern of behavior, you're going to be able to find a computation, lots of them, which would have produced that behavior. Okay. I get the second sort of concern is that pan-computationalism undermines the explanatory potential of our theories of implementation. I think maybe the best way to bring this out is to try to highlight the sort of contrastive character of at least many kinds of computational explanation. So what does explanation involve? I mean, it involves lots of things, but at least one thing it does is provide difference-making information. But under unlimited pan-computationalism, there really aren't any, at least any substantive computational differences between systems. Now we can sharpen this a little bit by distinguishing two kinds of explanatory scenarios. One is an intrasystemic scenario. Here you're trying to explain differences between, the actual versus the merely possible versus maybe even the impossible behavior of a particular system or system kind. So why does my laptop exhibit a certain performance profile when it's sorting? Well, it's because it uses, this sorting algorithm rather than another one. It's using heap sort instead of bubble sort. Why are certain kinds of sorting behaviors impossible? Well, it's because, for certain kinds of sorting algorithms, there might be lower bounds on their performance. So that's the intrasystemic scenario. You're just focusing on a single system or system kind. And then in the intersystemic scenarios, here you're trying to appeal to computations to explain differences between different systems or system kinds. So to take sort of a more cognitive science example, the fact that I can exhibit, more or less competent grasping behavior maybe is explained in terms of computation performed by my visual system. Someone with various kinds of cortical injuries might not exhibit the same sort of grasping behavior. They might have certain deficits. And one way, at least part of the explanation for that, might be that they're implementing different kinds of computations in the injured case. So broadly speaking, though, computational explanation at least often involves drawing contrast, but if, unlimited pan-computationalism is true, there won't be computational contrasts. And so it looks like these explanations will pretty uniformly fail. Okay, so here's the job description. What do we want a response to triviality to do? I mean, minimally, you might want it to do more than this, but minimally it should tell us how there can be computational discoveries, how the claim that a physical system implements a computation can be empirically contentful, how it can facilitate prediction and retrodiction. And also it should, let's say, vindicate computational explanation in the intersystemic and intrasystemic explanatory scenarios. By vindicate here, I just mean show that it's not a foregone conclusion that these explanations will fail. So show how there can be computational contrasts. Now, as I mentioned before, one way you can try to do this is to reject the simple mapping account. So there it is right there, and go for something a little more complicated. And the usual way to do this is to try to restrict the kinds of mappings that you're allowed to use. So, you say that a physical system implements a computation just in case the two are isomorphic and some X factor obtains. Now, here's a nice philosophical multiple choice problem, solve for X. And you can sort of imagine, you know how this goes. You might appeal to counterfactuals, you might appeal to causation, disposition, mechanisms, representation, information, theoretic notions, teleology, some combination of these, and maybe something else too. I'm going to try to avoid getting in that sort of debate, and I want to try to think about an alternative sort of way of approaching the problem. So I guess my orienting question is, what happens if we think of implementation really as a problem in the philosophy of applied mathematics, and in particular, can we use some very basic very basic insights from the philosophy of mathematics to try to reframe the problem. So, you know, I propose to begin at the beginning, which means, of course, starting with Frege. And one striking feature of what Frege says about number in the Grundlagen is really that physical stuff doesn't wear its numerical properties on its sleeves. Frege returns to this again and again. So he says things like, if I give someone a pack of cards and I say, find the number on these, I haven't yet given him completely the object they need to investigate. He needs some further word, cards, packs, or honors. Number cannot be said to belong to the pile of playing cards in its own right, but at most to belong to it in view of the way in which we have chosen to regard it. And so for Frege, you know, number applies to physical stuff relative to a concept. And sometimes, you know, when you don't pay attention to the concept that you're using when you're trying to account, you seem to be led towards things that sound vaguely similar to the kinds of things that folks who are trying to run triviality arguments seem to say. So here at the very bottom of the quote, Frege says, you know, if we don't tell someone, if we don't specify the concept we use when we try to count, anyone who did not know what we call a complete path would probably discover in the pile any other number you like before hitting on 2. So if you haven't specified your concept correctly, you might land on, or you might assign any number to the stuff in front of you. So what I want to try to do is consider how, you know, you might try to run a triviality argument against, you know, one of the most basic forms, or most basic applications of mathematics, namely whole number counting, and then try to draw a moral from that. Now, of course, you know, this, I'm not sort of the first person to try to draw parallels between the triviality arguments and other applications of mathematics. I mean, most notably, Ali Dresner and Bob Matthews have a very nice paper that draws connections between measurement theory and implementation. But as we'll see, I think I draw a slightly different conclusion than they do. Okay. So what would it take to trivialize whole number counting? Well, I take it that the operative claim in such an argument would be, let's call it pan-cardinalism. The claim that any expanse of physical matter can be assigned any finite count. And this is, I think, you know, part of what's lurking in the background for Frege. The thought here, though, is just given, you know, cleverly devised sort of concepts, you can assign any count you like to an expanse of physical stuff. So you've got your cards in front of you. It's one deck. It could be 52 cards. And then you have to start getting a little bit creative. Maybe you start counting, you know, fronts and backs of cards. Maybe you have to start counting half cards. But the thought here is that, you know, given a cleverly enough devised sort of concepts, you can assign extraordinarily many distinct cardinals to a given hunk of physical stuff. And so that would establish pan-cardinalism. And the question then is, you know, given pan-cardinalism, would this render whole number counting trivial? I think in this case, the answer is no. And it's pretty obvious why. When we are trying to count things, we're typically addressing what's called a numerosity question. So how many F's are there? And these kinds of questions are raised in certain conversational contexts, and these contexts tend to fix the relevant sortal that we should use when we're trying to count. Now, it's of course going to be true that if you use a different concept, you could arrive at a different count. If you're counting cards instead of decks of cards, you're going to get 52 instead of 1. But, you know, as long as you are bearing in mind the concept that you're using when you're counting, it's hard to see why the existence of different counts, which are generated by different concepts, would trivialize the claim that there is, you know, 52 cards in front of you. In a way, you know, the answer or the reason for this is that these alternative counts, especially, you know, the ones that you have to come up with from sort of highly gerrymandered sort of concepts, are really just answering questions that aren't being asked, given what we're interested in. If I ask you how many F's are there, tell me how many F's there are, not how many whatevers. Okay. So the broader point here and sort of background picture, and I think that the one thing I want to take away from Frege is just that mathematical notions apply to physical systems relative to a way of regarding that system mathematically. And of course, by varying the way that we regard a system mathematically, we can vary its mathematical character, or at least we can foreground different aspects of its mathematical character. That's a better way of putting it. So now I want to try to take that and translate it into the computational case. So what are these ways of regarding physical systems mathematically in the computational case? Well, I'm going to borrow some terminology from Jack from a paper in the 90s and call them labeling schemes. These will be utterly familiar. And what do these schemes do? Well, they do two things. They group, or they collect microphysical states into state types, and then they assign mathematical values, say a string or a number, to that state type. And so a labeling scheme, there are these sort of two dimensions of variation. You can tinker with both because you can tinker with your groupings or play around with your groupings, and you can tinker around with the way that you assign mathematical values to those groupings. I'm just going to treat them here, though, together, and just say that a labeling scheme is, the composition of a grouping and a labeling. So when we're thinking about implementation, the, let's say, moral I want to draw from Frege is that really there's a kind of relativity here. Call it the relativity of implementation. And so the operative notion isn't, physical system implements some computational model, rather it's physical system implements some computational model under or relative to or in light of some appropriate labeling scheme. And I think, this kind of relativity is very aptly illustrated by the sorts of indeterminacy cases that we are all at this point familiar with. So we have our tristable gate. Under one labeling scheme it implements, and under another labeling scheme it implements, or it's a true fact about the tristable state that relative to one, it computes one logical function, and relative to the other labeling scheme, it computes another. These are both true of the gate at the same time, in just the same way that, the deck of cards is both one deck and 52 cards at the same time. These aren't incompatible claims. So, I think this kind of relativity was in a way sort of implicit in Jack's description of the situation the other day. Although for Jack, there's a sort of, or at least in the talk the other day, what was going on was sort of downstream from the kind of point that I wanted to make. So I take it one of the take-home messages from Jack's talk is that you can leverage what Jack called multi-availability in different ways by using different sorts of, say, probing devices. And I guess what I sort of take from Frege is that, computation can be determinate relative to a labeling scheme even before we start the mechanizing process. So the question is, how do we tap into these different kinds of labelings? That's where the point that I think I'm making, feeds into the mechanizing process, but in a way it's sort of, it's upstream. Okay, so how does all this help with the triviality argument? Well, the first thing to notice is that when a physical system implements every computational model, it does so relative to a distinct labeling scheme in each case. This is pretty clear if you look at Putnam's original recipe. When the rock sitting in the sun implements, the three-state ABA automata, it uses one labeling scheme. When it implements the five-state ABA automata, it uses another, and so on for the rest. What Putnam gives us is a recipe for cooking up labeling schemes for particular automata. But I guess what I want to say is that, the fact that a system implements multiple distinct computations relative to different schemes doesn't automatically show that descriptions framed in terms of a fixed scheme is trivial in the sense of being descriptively or explanatorily inadequate in the ways that I tried to outline earlier. In a way, I think this is sort of, hard to see if you're only focusing on the rock, because the rock really exhibits not much in the way of interesting macroscopic behavior. And so there's a sense in which, it's like arbitrary to work with any one of these labeling schemes over any other when we're trying to describe the rock computationally. And this might even be the right conclusion to draw in the case of the rock. There might be no non-arbitrary way to describe the rock computationally, given our descriptive and explanatory interests with respect to the rock. But what does this show us? At best, it shows that the rock is not fruitfully understood in computational terms. I don't think it shows that there can't be non-arbitrary grounds for preferring other kinds of labeling schemes when we're trying to understand other sorts of systems. So, the problem with the computational description of the rock, it's not that these are false descriptions of the rock. They are true descriptions relative to their appropriate labeling schemes. It's just that they're very boring and scientifically uninteresting. So here's the sort of diagnosis. In the computational sciences, we're concerned only with specific kinds of physical systems and specific aspects of their properties and behavior. And so given that, relative to a fixed labeling scheme, a system will implement the unique computational model, or at least Putnam and Searle haven't given us a reason to doubt that much. The question then should be, well, are there non-arbitrary grounds for working with one or another kind of labeling scheme when we're trying to understand these systems computationally, given our theoretical goals and interests? And again, I think, it's useful to bear in mind the analogy with the number. Can there be non-arbitrary ways of counting physical stuff given our goals and interests in providing a particular count? That's the type of question you should be asking. Okay, now I'm not going to try to give you sort of a totally, anything like a totally worked out story about whether there can be non-arbitrary grounds. So what I want to do just for the next couple minutes is sort of gesture broadly in the direction of the sorts of considerations that might get into the picture. So when we consider artificial computing systems, for instance, I mean, these are designed to compute specific logical functions while meeting various design criteria. They need to be reliable, modular, not consume too much power, have certain performance capabilities, and so forth. And so given these sorts of goals, it's, eminently reasonable to describe them in terms of the kinds of labeling schemes that, for example, their engineers have in mind. Because it's precisely under that kind of labeling scheme that they can fulfill the role that we expect them to in our computing practice. Now, in some cases, there can be a little bit of slack between, say, the groupings that we get from computer engineers and the kinds of labelings that we ought to use. So, fix your groupings. You can still vary the interpretation of what counts as a logical 1 and logical 0. This kind of slack is, I guess, just taken up by conventional considerations in most cases. Nowadays, a high state is logical 1 and a low state is logical 0, but that's not, inevitable, right? There are, in the history of computing, examples of systems which use the reverse assignment. So the Atanasoff Berry computer, that's a replica of which is in the corner right there, used the reverse assignment. But the thought is, the fact that even though my laptop implements, let's say, every computational architecture under some labeling scheme or another, doesn't mean that there can't be good reasons for describing it in terms of a very specific one, say like an x86, sanctioned by a particular labeling scheme. Okay, in a way, that's the easy case. Natural computing systems, here it's, much more difficult. It's not often an open empirical question, just which scheme is appropriate for theorizing about some system. And there are a range, maybe a range of plausible schemes that are consistent with the available data. So we're going to, appeal to really, I think, the sorts of considerations that Lotem emphasized in her talk the other day. You might need to appeal to behavioral data, causal or correlational information, etiological or anatomical facts. These are all sorts of things that can bear on your choice to describe a system in terms of a specific kinds of labeling scheme. Again, it's not, a matter of free interpretation or totally arbitrary in the way that, say, Searle would suggest. Okay, so what about the usual suspects, these causal, counterfactual, representational, mechanistic, and so on restrictions? I guess on the sort of view that I think that I've been trying to sketch out, it suggests a kind of shift in focus for how we think about these proposals. So don't think of these as global restrictions on mappings. We don't need global restrictions once we build in relativity to implementation. What we should think of them as, or we should think of them as proposals about how we ought to label systems for specific phenomena of interest. So given our descriptive and explanatory interests with respect to a particular kind of system. So it may be that for certain kinds of targets, we need to use a labeling scheme that somehow keys into the semantic properties of a system in the way that the semantic theorists have emphasized. In other cases, however, we may not need to do that. It may be enough to get by with just mechanistic structure. But it's going to come down to the sort of, I think, key shift in focus is to not think of these as proposals about like the nature of implementation or the nature of physical computation, but rather, the nature of implementation is given by the sort of relativized simple mapping account. Instead, think of these as proposals about how to identify the labelings you ought to use to understand a system. And so one potentially nice corollary of this is that it turns out that these accounts need not compete as accounts of implementation. They can compete when it comes to whether they're adequate for describing a particular kind of phenomenon. So, there might be a genuine question about whether some phenomena needs to be characterized semantically or non-semantically. But that's not, that's not a question about implementation. That's a question about how should we describe this system in terms of a particular kind of mathematical formalism. Okay. So this is just sort of crossing your T's and dotting your I's. I mean, once you've fixed a labeling scheme, it will turn out to be an empirical question whether a given system implements a given computational model under that scheme. So consider, the AND scheme on the right. We can determine empirically whether a physical system implements an AND scheme relative to a particular kind of labeling scheme by determining, for example, whether it transforms, I guess in the case of like a digital computer, electromagnetic properties in the right sorts of ways. Again, for the explanatory criteria, the key thing to notice is that relative to fixed labeling schemes, there can be computational contrast. So relative to, just to work in this sort of case, relative to the AND scheme, it's a fact about, that tristable device that it implements and not or. And so we can explain why, output 0 when you give it 1 and 0 by bearing in mind that particular labeling scheme. And that explains why it doesn't output 1 when you get it 1 and 0. The difference comes down to typically labeling. So that's to say there can be computational contrast. Okay. So I've got just under 5 minutes remaining, so let me say something about observer relativity. So in a way, the response that I've been exploring, it kind of bites the bullet on pan-computationalism, but it takes the sting out by making this sort of relativistic move. And I think once you make that sort of move, you can at least, you're not committed to observer relativity. And what I want to do next is just think about, a few different senses of observer relativity and to point out that this kind of relativistic mapping account isn't committed to them, or it's not committed to any but a very sort of weak and uninteresting version. Okay, so the first kind is what I'll call, for lack of a name, object level observer relativity. So I think this is what Searle has in mind when he says things like, computations are not the eye of the beholder. It's the sort of thing that Schweitzer has in mind when he says that computation depends on an active ascription from an external observer. And the thought, very roughly speaking, is that, observer relativity gets in at the level of either labeling schemes or computations themselves. It's, a physical system doesn't compute unless an observer takes the right sort of attitude towards it, engages in an active description, whatever. And so the striking thing about this move is that it's very reminiscent to a move that Berkeley makes. He makes it a few different times, partly in the New Theory of Vision. Here's a quote from the Principles. And so here's what Berkeley says. That number is entirely the creature of the mind, even though the other qualities be allowed to exist without, will be evident to whoever considers that the same thing bears a different denomination of number as the mind views it with different respects. Thus, the same extension as 1 or 3 or 36, according as the mind considers it with reference to a yard, a foot, or an inch. Number is so visibly relative and dependent on men's understanding that it's strange to think how anyone could give it an absolute existence without the mind. Frege takes Berkeley to task for this in the Grundlagen, and he points out that this is just a non sequitur. The fact that we can fix our attention on different sorts of counts doesn't show that number is observer relative, a creature of the mind. It does show that it's relative to something, but there's room here for an alternative. Frege gives us one. It's the view that number is relative to concepts, and on sort of a broadly Fregean view, these concepts are mind independent. So the thought would be that you could say the same, something very similar in the computational case. Labeling schemes are just, at the end of the day, functions. These are functions from states of physical systems to mathematical structures, and these functions will exist, or at least, let's say there's room in the philosophy of mathematics for thinking that these exist independent of acts of ascription. Of course, you could have, maybe a kind of anti-realist view in the philosophy of mathematics. That's like, that's a live option, but it's not mandatory, is the point. Okay, so I don't think we're committed to what I was calling object level observer relativity. I think there's another sense of observer relativity that we should consider. And it's not that like computations or labeling schemes are in some sense observer relative, but it's that, it's something about the fact that, well, I'll put it this way. The only reasons we could have for preferring one kind of labeling scheme over another really are grounded in facts about us. And I think this kind of suggestion is at least hinted at near the end of the paper that I mentioned earlier by Matthews and Ellie. So they write that the crucial requirement on computational implementation is that of supporting and enabling surrogative reasoning and conceptualization. This is precisely where the imagined computational implementations proposed by Putnam and Searle fail. We can neither reason nor conceptualize surrogatively with either. Now, I don't want to sort of be too critical about this because in a way, practical surrogativity is kind of a promissory note, and it's a suggestion that's floated but not sort of spelled out at the end of the paper. But I guess what I would want to point out is that, at least on a narrow understanding, there can be more to computational ascription than practical surrogativity. I mean, computational ascription, scientific ascription, more generally, can be guided by all sorts of considerations. Truth, for example, faithfulness to data. It might be that to get a very accurate representation of a system, you have to come up with representations that are horrifically complicated to work with, perhaps so complicated that they're really not tractable. So here the thought is that when we ascribe computations to physical systems in terms of specific labeling schemes, this should be guided by, or will be guided by, general theoretical ideals, simplicity, fruitfulness, blah, blah, blah. And these need not be identified with something observer relative, even in this sort of meta level sense about which labeling schemes we use. Okay. Now there is a utterly trivial sense in which the labeling scheme we use is observer relative, namely the one we use and the one we in fact focus on will depend on facts about us. It's hard to see how it couldn't, but this I take to be true of scientific representations quite generally. And I'm not clear that we can, draw an inference from this to any of the more potentially contentious versions of observer relativity I just identified. Okay, so let me wrap up. What does this get us? Well, one is that in a way, metaphysical concerns are sort of downstream from triviality worries, or at the very least, it looks like there's a way to kind of take the wind out of the sails of the Putnam-Searle argument without giving a robust metaphysics of implementation, without giving a restricted mapping account. It's enough to notice that physical systems implement computations relative to labeling schemes. It also gives us a principled way to potentially unify extant responses by showing that they needn't compete as accounts of implementation, rather they're proposals about how we should describe systems computationally. I haven't argued that implementation is always non-trivial. Sometimes it might be. Putnam's rock is a case in point. There's just kind of no non-arbitrary way to describe the rock computationally. That doesn't show that there can't be other, that computational notions can't be used fruitfully in other cases. That just shows us something about the rock. And I also haven't really said much about how we should be applying computational notions in particular cases. In a way, this is sort of, work on the agenda. But I've only really very roughly gestured in that direction. Okay, so if you want a positive upshot, let me put it like this. It's that we should be asking slightly different questions. So instead of asking, what is it for a physical system to implement a computation, you should ask, what kind of labeling scheme will best serve our descriptive and explanatory interests with respect to some phenomena or class of systems that we're trying to understand. Instead of asking questions like, is computation trivial? Is unlimited Penn computationalism true? Ask, are there non-arbitrary grounds for describing this system or this kind of system computationally? That's all I've got. Thank you. Orly?
Thank you for a beautiful presentation. Since I agree with almost everything you said, I have this next question.
Yeah.
So you say that computation is following Searle in the eye of the beholder, or following Berkeley, the number is a creature of the mind, or you say that the labeling scheme depends on us, etc. And my question is the following. That's all fine, as long as we're interested in the question, what computation does this implement? But if we turn our attention to the computation, which is the cognition, so that's us. My question is, who is or what is the beholder or the mind or the us that selects or fixes the labeling scheme in the brain, as it were, that makes this computation us? Is there a super observer looking at us, or what is it? What makes it?
So, two things. So I don't think, or at least I don't think I'm committed to thinking that computation is in the eye of the beholder. I think this is actually optional on the view that I've outlined.
All right. So
What I do think is that it's relative to a labeling scheme.
fine.
But you can tell different stories about how labeling schemes work. So one option is like the Putnam, or well, Putnam doesn't really say this, but like sort of the Searle Schweitzer story. Labeling schemes only exist if they're, we ascribe computations to systems, blah, blah, blah.
Right.
But I think sort of one of the moral I wanted to take from Frege's response to Berkeley is just that that's not mandatory. You can have a view of labeling schemes according to which, they are as mind independent, their existence is as objective as you might want. And obviously the Freudian concept. Okay.
All of them
Yes.
exist.
Yeah.
Right.
Yeah. So when it comes to philosophy of mind, I mean, I guess what I want to know is, tell me a story about what you think the mind is and what mental processes consist of. And then we can see if there's going to be a labeling scheme that can fit that job description. So, I take that to be sort of a problem in the philosophy of mind and not a problem for theories of implementation. Tell me a story about the mind, and I can tell you if there'll be a labeling scheme that can underwrite that story and maybe support a version of computational functionalism. But again, I want to say that sort of stuff is like downstream of the implementation per se. Does that help?
Well, I'll continue later.
Okay.
If there is time, I'll continue this.
Sounds good.
Yeah, I think you made a really interesting kind of shift of perspective there. And I guess on your relativistic account, there are sort of these two extra indices or parameters. There's the labeler, and in the background, there's, you know, their interest, their project in hand. And then there's the labeling scheme they select. But I think the difficulty with kind of like throwing the emphasis in that direction the way that we have is that labelers can have all sorts of kind of crazy interests. You know, Searle is an example of a labeler. And you know, you may have all sorts of kind of you know, philosophical agendas, and they're the project in which the labeler chooses their labeling schemes. So I think in a way your shift has kind of changed the form of the problem, but not really its essential nature, because now it's a problem about which you know, which labelings are reasonable. It's the problem of distinguishing like honest labelings or honest models from you know, the ones that we don't want to consider as you know, reasonable scientific labels. You know, they mustn't hide information. They mustn't be ex post facto. There must be something about you know, temporality, you know, temporal relations being appropriately observed and so on. So all that stuff that you had down the left-hand column in an early slide, kind of the need for a theory that recruits some of that stuff just re-arises in trying to distinguish honest labelings from you know, labelings nearly philosophical interest or things like that.
So maybe I can say something about my motivation that will illuminate why I'm sort of framing things the way I do, because I completely agree. Like, look, the stuff that people have been worried about and the sorts of proposals that we find in the literature in like the last 30 odd years, I don't deny that you need that stuff at some level. The question for me is, how is it fitting into the picture? The usual way of framing the problem is of giving a theory of implementation, a general theory of implementation. This is like, for example, the way Chalmers sort of talks about it in like his papers in the 90s. And, you know, I guess it seems to me that that's not the right sort of question to be asking. What we have here is a case of, you know, a branch of mathematics, which is being used to describe certain kinds of physical systems. We don't need to tell, I mean, no one would impose, I take it, a kind of restricted, a restricted account of counting that, you know, the only the only sort of physical magnitudes in the world are ones that satisfy some analog of a restricted mapping account for the cardinality case. No, we just say you can count if you know, there are n things if you can line some objects up with, you know, say first n cardinals. And then we shift questions about which things we should be counting over to, you know, a specific investigative context. And that's going to, and there you get into questions about, you know, what kinds of things are we using? And so I guess, or what kinds of things are we counting with? And so I guess I'm trying to carry out a similar sort of shift in focus. Don't ask what is implementation. Don't ask what the nature of implementation is, because that's really like the way these debates are typically framed. Instead ask, you know, give me an explanatory target and tell me what you think you need to get a grip on it computationally. So in that sense, you know, I completely agree that I haven't, in some sense, solved the triviality problem in the sense of showing you that for any given, you know, target, there's going to be, I haven't told you what that story is going to look like. And it will definitely appeal to the sorts of causal, counterfactual kinds of relations that are all over the literature. But I think there is, I don't know, it seems to me that at that point, we're asking a very different question, and the nature and the sort of rules of the game have shifted a little bit, because now we're asking, you know, how does this kind of mathematical scientific explanation work? How do we use it to get a grip on this kind of system? And we're not asking questions about the nature of implementation or about what implementation is. So that's just to say, that's sort of the kind of shift that I'm trying to carry out, and why I think it's, you know, a useful one. It's I wouldn't exactly call it a matter of like metaphysical bookkeeping, but that's kind of what's going on.
Yeah.
I don't know if that helps.
Right.
Yeah.
And you sort of push one problem over the cliff.
Yeah.
But there's another problem that remains, as we're saying.
Yeah.
And it's kind of a much healthier and much more interesting problem
Yeah.
than the one that you pushed over the cliff. And it's, how do you distinguish between honest labeling and not honest labeling?
And so what I want to say is that sort of debate can be carried out sort of absent worries about pan-computationalism, absent worries about triviality. We can sort of leave that behind, or at least that's the hope. But yeah, there's still a question. Still work to do.
Yeah, thank you. It was great. I want to continue, basically, Jen, and maybe be even more provocative with, if you change the framework, and now the question is, talking about labeling, honest versus non-honest labeling. So now you can see the role, not just as computing every computable function, but actually also computing non-computable function and solve, NP hard problems in polynomial time, etc., etc. So, yes, so we still want to say something about this, namely to put some constraints on, on the labeling if we want to talk about computation. You can leave implementation aside, but we want to talk about computation. Now, I think that Frege, I haven't read him for a long, long time, but he had a fairly strict notion of a restriction on what counts as a concept. I mean, not every, every description, there were some constraints on description that you can count as a concept. So not everything goes. So I think that for him also, wouldn't say everything could describe or assign numerical values to the back of cards, but I'm not sure that everything, every sort of cardinality, etc. So yes, but at the end, if you say, okay, let's put constraints. There should be constraints on labeling or something like this. It's another project, etc. But if you accept this, so at the end of the day, so maybe for you, and computation is implementation plus X. Just your X is something else, but that's added to the list of dispositions, countervectors, etc. You have simply another suggestion. I mean, if you think that there are constraints at all on the labeling, in principle, of course, in the everyday life, I agree that we come with our constraints and interests, and in principle, we think that someone else would come with very wide labeling schemes.
So good. So let me say a couple of things. First, I'm not a Frege scholar. I just want to use him. I just want to get enough Frege on the table to make some trouble. So I don't claim that Frege would, agree that you can assign any count. And sometimes he sort of says things that, you could see him that sort of suggest going in that direction, but it makes no difference to, I think, what I'm saying, whether he actually thinks that. Okay, so that's the correct point. So yeah, I mean, one thing I want an account of implementation. So I want an account of implementation to be flexible. And I don't want to have to say things like implementation always involves, say, semantic, or computation always involves semantic properties, or mechanistic properties, or whatever. It seems to me that in a way that's sort of putting your neck out when you don't have to. Tell me a story about a particular kind of explanatory target, and then we can have a discussion about, do we need semantic properties? Do we need mechanistic properties? How do those interact? What's the labeling that we should use? But again, it's a different question at that point. We're not asking about sort of the nature of computation. We're asking, how do we describe the system computationally to serve some theoretical interest? One other thing about I guess two other things. So one about the labelings, I mean, the terminology here isn't great because labeling suggests, I think as Jack put it, a labeler. And I don't think that you actually need like labelers in the sense of agents or anything like that. Just think of these as sets. You can do this all, you know, with some pretty modest like impure set theory. You just need to be able to group physical states together and then take them to some mathematical object. That's what the labeling does. You don't need labelers in the sense of, you know, individuals who are going and labeling or making these assignments. Although individual labelers could come along after the fact and pick out individual ones that they're interested in the same way that we can come along and use particular concepts to count. Yeah, so, and then I guess the final thing is, you know, could we interpret the rock as computing some uncomputable function? Maybe, but tell me a story about that lines up in, you know, tell me a story about that will interface with computer scientific practice in a way that computer scientists will find engaging. It seems like there are constraints on the kinds of, say, notations that we use, say, in computer science that make those sorts of cases rather less interesting from a computer scientific perspective. In a sense, are the labelings there? Yeah, just in the way that all the numbers are there. But, you know, try to build a computer that leverages them. Yeah, but again, that's not a question about implementation. It's about, does this interface with the practice? Okay.
Last question is yes. Okay, on the brainstorm, probably it's a continuation of what's already been said. I mean, it's on one hand, it's very nice. You have this ecumenical view, so very peaceful, and you know.
That's what I'm hoping for.
But of course, it brings the classic problems of ecumenism. Because, so here's the issue. I mean, sometimes I may just have different preferences at the same time. I mean, sometimes I'd like to have my labeling to be predictably precise, at the same time to be efficient, and you know. And so I don't know what to do. And also, you know, you're sort of saying that discourse will collapse because if you come up with a labeling, I'll tell you, I don't like that. It's not good. You know, you would say, yeah, okay, there's no more to talk about here. But it seems that there is something to be talked about. So, so it sounds very peaceful in the beginning, but at the end, it seems that you're also getting into not very pleasant consequences because these things seem to be relevant. So if I can't reach a conclusion because I have different competing preferences, I'd like to ask someone who knows better, and I can't get an answer. And if I disagree with you, I would like to talk about it, but you would say, no, we can't really talk about it, it's just my preference. I'm not sure that's something you would want to accept.
So is the worry that folks might just wind up talking past each other if they use different labeling schemes?
Just stop talking.
Yeah, well, I mean, this is, so one thought is that it's not clear that there's sort of a problem unique to computation here, once we make the sort of move that I've suggested. There's always going to be a question about what kind of scientific representation we should be using, at least sort of mathematized scientific representation we should be using to describe a certain kind of system. Scientists disagree all the time about how they should describe a system, and it's very sensitive to things like, you know, to what extent are we trying to say idealize with respect to the system? How much do we want an accurate representation? How much computational power do we have available when we're working with a certain kind of representation? There could be cases where scientists are using different representations and they have different sort of goals and standards with respect to how they're investigating the system that they wind up talking past each other. I guess I'm inclined to say that that's kind of a fact of, you know, that's life. Sometimes, you know, if I don't tell you what concept I'm using when I count, if I say, give me 3.
I think you're more radical than that. You know, saying sometimes we fall past each other. We're saying in a way we shouldn't even be talking.
I don't think so, because I think there is a way.
So I understand what you're saying.
Well, I think, let me disavow any interpretations along that line then. What I think people should do is be clear about the labeling scheme that they're trying to use for a specific kind of phenomena. That's where the action is. People could talk past each other if they're using different labeling schemes. But if, you know, everyone's on the same page, as it were, we're all using the same concept, it seems that if there can be, I would hope, some sort of successful communication, but
Let's start the next session. We have Near Fresco, delivering a talk that's co-collaborative with Mark Artiga and Marty Wolf called Wide Pseudo-Functional Individuation of Computation.
Sorry, and thanks the organizers for this lovely conference workshop. So yeah, let's just get started. The title basically says very little. I keep changing it all the time. It's not very informative. So what's the topic? You have a problem of indeterminacy, or maybe not, as Jack told us yesterday. And I'm going to be talking about one way of individuating computation, and that's using functional considerations, functional factors. I'll start by giving you some background about the indeterminacy of computation, just in case you still don't know what it's all about. Maybe I don't know what it's about. I'm going to give or show a couple of toy examples that exhibit the sort of indeterminacy that I want to talk about. I'm going to introduce two dimensions of functional individuation, and I'll argue that this is important for the functional individuation that I have in mind. Then I'm going to suggest that there's a good chance that the indeterminacy of computation dissolves if it ever was a problem, and I'll try to do it without invoking semantic content. I'll talk very little about this. It all depends on how we go with time. Okay. So again, just in case you haven't heard about the indeterminacy of computation before, in the classical sense, I'm not talking about quantum computers. Where's Orly? She disappeared, or she's here? Good. No quantum computation here, please. So the idea is that a single classical physical process taking place in whatever system we have in mind may often be described equally well as computing several different functions, right? I mean, we all keep talking about Boolean functions, but it need not be the case. There can be far more complicated mathematical functions, and even there, the issue of indeterminacy arises. And the reason this seems to be a problem of indeterminacy is because there doesn't seem to be any fact of the matter about which of these descriptions is correct, or in other words, what is the computational identity of that system, if indeed it computes multiple mathematical functions. By the way, I'm going to switch quite a bit between mathematical functions and biological functions. Hopefully I get it right. So in terms of this problem or phenomenon, the constraints that we might need to determine the computational identity of a physical system or physical computing system, like Andre suggested or reminded us before, there might be various constraints or a combination thereof. So we can talk about causal factors, counterfactual factors, semantic factors, functional factors, and so on and so forth. I'll assume today realism about computation, so we'll go with some of the metaphysical constraints. So Dimitri here suggested that functional constraints are sufficient for individuation, even in the face of indeterminacy. Gualtiero, that we know and love, thinks the same, but he left, so I won't say much more about it. And recently also Tucker, when he presented a very nice analysis of the phenomenon of miscomputation, very important phenomenon, by the way, that's just marketing, because I'm writing another paper. So he also accepts this idea of functional individuation, very narrow one. You might have heard that name before. So there's a person by the name of Aron and a person by the name of Mark Spivak, who think that those constraints are semantic, right? I'll try to say a little bit more about it. What we want to argue, and this is not royal we, that's with Mark and Marty, We think that this problem, if it is a problem, actually dissolves when we consider the phenomenon in question from the right functional perspective. So there are various ways of looking at indeterminacy, even when we leave aside for the time being the indeterminacy that results from labelings, right? I mean, we can argue about whether Slutzing and Oroning are two sides of the same coin or not, whether labeling schemes are, relevant or not in computational cognitive neuroscience, etc. I'm not going to enter the debate. So there are various ways that we can actually group together physical states or physical features of the system, and then we abstract for them in order to get to the computational states or features or processes that we want. So we can talk about physical properties that occur at different times within a particular system, right? And then we can do it relative to the particular timestamp. We can talk about even different properties of the same system that are grouped together, right? So we talked about voltages a lot. We can say we can use voltages and barometric pressure, or voltages and cosmic rays, whatever. And somehow we can group them together and say, voila, these are the relevant physical states, and we can map them onto computational states. The properties I'm going to talk about today, or more correctly, the way of grouping that I'm going to talk about today, is basically saying that we have the same physical properties at the same time in the same system, right? This should all sound very familiar to you by now, okay? And that's the version I'm going to focus on. Okay. So again, Oron, if a system implements different automata concurrently, there must be a constraint that determines which automaton is taken into account by the computational taxonomy in a given context. Yada, yada, yada. This constraint is, at least in part, a semantic feature, namely the contents of the states of the physical system. Okay, so I think this presents the problem very clearly. Dimitri basically says something slightly different. It is functional rather than physical structure that individuates computational states and processes. Maybe I should just give some context for those of you that maybe are unfamiliar with the way that Dimitri responds to some challenges that arise when we accept kind of mechanistic individuation that is proposed by Joe Dewhurst, the same person that Marcin mentioned before, who is no longer doing philosophy of computation, unfortunately, but he found something more interesting to do. So continuing on, so Dimitri tells us that regimented input-output transformations, okay, of what he calls equivalence classes of physical states across the system is what computational individuation requires, okay? So you can basically look very narrowly at the system, look for those equivalence classes of the relevant physical states, and then this is all we need for individuating the computation performed by the system. So Gualtiero, now I can say whatever I want because he left, claims that contextual factors may also play an individual role in determining which computation is performed. But he claims that, or at least in the 2015 book, he claims that those factors are limited to the immediate environment with which the system interacts. Okay, so now moving on to some examples of computational indeterminacy. So Andre, you had like the multiple choice question. Can you guys guess which system we have in mind? You guessed it correctly. The tri-stable or the tri-state system. Excellent. That's why I can now move on quickly. Da 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 da. You get the picture? Good. I'll add here that in the paper that I think also appears in the version with Jens. Input outputs, nice. And we have another way to look at the motor output. Okay, so we look at the output channel of that system. We see what the groupings give us in terms of the outputs. And then we say, in this case that we have three different possible outputs in terms of the arm movement, okay, that we see connected to that state, to that system, sorry. So we individuate anything lower than 45 degrees as no movement, anything between 45 and 90 as medium movement, and large movement is only when we go above 90 degrees. I don't need to elaborate more, right? I mean, we just take those three states and we group them together such that we get a binary system basically instead of a tri-stable or a tri-state system. Now, the idea is this: the movement or the motor movement can be identified with either large movement, okay, only greater than 90 degrees, or when we say medium plus large movement, okay, so it's just a matter of whether low and medium go together or medium high. Same story as before, I'm just connecting the arm movement to the picture. And then Jensen or Ron say, so even when we do this, they say the system plus its immediate causal environment are not sufficient for fixing the actual computations performed by the system, okay? So if we thought that we can just look at the system in its immediate context or the immediate environment, that's not enough. I think Oron presents a nice challenge for functional views. I'll read the last part. The quote is longer, origin, or it was longer. We can group the same physical states into different formal types in different ways, possibly even to include the wider functional effects. But a functional account should show us how the wider context helps to avoid indeterminacies without referring to the content of the system's state. If I'm able to propose such a solution without appealing to semantic content, I'm happy enough. We'll see if Oron is happy with that as well. Okay, now moving on from the familiar, I can just use that screen. Moving on from the familiar example to another one. Now I'm moving away from voltages to light intensities, okay? And let's just say for sake of argument, the fine grainness that we need is basically either no light or little light or strong light, okay? And let's assume that we have an organism, plankton in this case, that has two input receptors, right? It's a toy example. I make no empirical claims about how plankton actually work, okay? And we can just say that very similar to what we said before about the motor arm movement. We can say that when we have no light and low light, there's no movement, okay? Very similar to the 0 to 45 degrees before. Any combination of those basically give us sideway movements, okay? So we just move to the sides. And only when we have strong light and strong light does the plankton just moves upward to say the water's surface, okay? So basically we want to claim that this is an analogous way of describing a similar system, okay? So one way of going about it is to say, take the no light and little light together, group them, say this is logical 0, okay? And then say that strong light is typed logical 1 or sufficient light, okay? That's one way. So this is equivalent to the low and medium, okay, and the high by itself. And the other option is basically saying that little light and strong light are grouped together as sufficient light, okay, that's the logical 1, and the no light is insufficient light. So that's basically the other way around. So this is what we start with, have those groupings in mind, and voila, you get this. Anyone cares to gesture at what this is? It's an AND gate, yes. Yes, okay, I was being sarcastic. I thought everyone would say it together, but anyway, this is an AND gate. Perfect. This is the other way of grouping when little light and strong light are typed together. let's save the effort. This is an OR gate, okay? So it's slightly different than the example that Oron showed before, yesterday, right? So yesterday showed us a distinction between XOR and OR. The details don't really matter. We'll just go with AND and OR. Okay. So the indeterminacy supposedly is still there. Now let's see if functional individuation can deal with such indeterminacy. Okay, so the idea is this. Now we're talking about an organism, right? That responds to lights and somehow moves in the environment. Okay, so we might say, like what we said before about the tri-stable gate and the R movement, the very same organism, okay, using a particular subsystem, okay, may compute conjunction in one context, disjunction in another context. You want ORing and XORing, doesn't matter. That could work as well. We just need to change our toy example a little bit, okay? So then what we say in terms of a functional description of what this organism does, then we might say that when it's doing a conjunction, the behavior spotted in the environment is basically sick food behavior, okay? And let's assume for the time being that the plankton can only feed off whatever there is at the water surface. Again, maybe not very plausible empirically, but let's assume that for the time being. And it computes disjunction at another context, okay? And this is when it wants to disperse from conspecifics. They all compete for mates or for food or for, I don't know, good coffee places. So they just disperse from the conspecifics. Why is this important? Simple. If we go back to the account that Gualtiero puts forward, we have a relatively narrow individuation, right? It's wider than the one that, say, Viewers proposes or Dimitri or Tucker, okay? But even then, his individuation is rather narrow, but the argument would be that we can appeal to wider ecological factors and then basically see which computation is taking place, still without appealing to content. Okay, now the question is, fine, but there are different ways of carving out functions. So what kind of function can do the job in the face of such indeterminacy without also appealing to semantic content inevitably, okay, semantic content of the relevant computational states. So here we suggest that before we can talk about the relevant functional context, we need not just to distinguish between narrow and wide function, okay, but also between proximal and distal function, okay? So we have two X's. So here's another illustrative example. Now, we kept the example relatively far-reaching or something that might even involve representation, some might argue, but we don't need to appeal to all such properties. This is just to make the distinction between wideness and narrowness and proximal and distal features more clearly. Okay, so let's assume that this amygdala here is the system that we want to individuate. Okay, and let's suppose that it performs computations. So let's look first at the size of the inputs, right? So we can say that, for example, V2 neuronal activity might be some relevant input process going on here because V2 connects directly to the amygdala, for example, okay? So this is very proximal, okay? So here we're dealing with a narrow input, right? It's still within the boundaries of the system. And it's proximal because it's directly connected to the amygdala, okay? We're still within the narrow realm. Now we say, okay, let's assume that there's some kind of photoreceptor activity, okay? So we're now further away from V2, further away from the amygdala. We're still narrow, but in terms of the proximal distal axis, this is more proximal, this is more distal, and the more we move here, it becomes more and more distal, okay? So it's like a gradual distinction and not a dichotomous one. So now we might say that the input to the system is some kind of large visual stimulus, okay? So what basically triggers the relevant photoreceptor activity is, I don't know, say a large object, right? Large scale object. And this is more distal than the photoreceptor activity that can happen due to different types of stimuli. And then we can go even further than that and say, let's suppose that we're now actually responding to not just a large visual stimulus like, I don't know, a refrigerator, but a bear, scary bear, okay? So we might want to keep our distance. Okay, so this is basically very distal. We can do the very same thing with the outputs, okay? I know, Martin, that you were talking today about inputless and outputless computations because we're dealing with, or at least I want to be dealing with organisms. I think inputs and outputs are important. So again, in terms of outputs, we might say that as a result of whatever activity of the amygdala, we've got some serotonin activity or serotonin being produced. So that would be very narrow, okay, very close to the system in question. When we go more distal, we might say, okay, now whatever the amygdala is doing or whatever signals it sends out, this might actually result in terms of the outputs, some muscle contraction, okay? So that's still within the boundaries of the system, right? So when I'm flexing and expanding my muscles, that's still within the system. And, you know, I can do that whether I just want to stretch my muscles or when I want to lift a weight, just because it's fun to do while you're giving a talk. And you can then go wider, right? So now, once we leave the boundaries of the system, we might say, okay, so when we look at what the organism does from a wider perspective, then what we see in terms of the motor output is actually running. Okay, so the organism somehow runs in the environment, but you know, I might run for fun. Some people do that, or I might run when I'm escaping from a bear. Okay, so the running is the same, but the reason or the context in which I run might make a big difference in terms of what the organism does and whether it survives. How am I doing for time? 20 minutes. Fine. Okay, so going back to what Gualtiero says about it. Pause. So I'm getting 10 more seconds. A functional property is wide, just in case it supervenes on both what is inside the boundaries of the system and some portion of the system's environment, which he says may simply be a larger system that contains it, right? Because we're talking about subsystems and they may be bigger systems are all that we need. And then Gualtiero says when we consider the case of organisms, okay, the wideness of the putative computational properties that we need to concern ourselves with. In the case of, say, nervous systems, that doesn't even reach into the organism's environment, and he says only sensory receptors and muscle fibers. Okay, so still within the same organism. But we say that it is actually when we consider distal ecological factors, it's when we can actually discover, as in the case of the running example, right? Running for the sake of, I don't know, exercise and running for the sake of saving my life might be different. And that's why appealing to the more distal considerations might result in discovering the different adaptive behaviors, okay? That in our case might be the ones that underpin the computation that the visual motor system performs here, right? So it might be conjunction and disjunction in our case. The reason I say that is because if we just look at the muscle fibers and the photoreceptors, that may not give us the right computational function in every possible context. So now let's go back to the toy example that I started with. So let's suppose that we want to see why performing conjunction can be adaptive with respect to that plankton. Okay, so in a conjunction scenario, we might say that the plankton seeks food only when it reaches the water surface, or it only can get food at the water surface. Okay, and so it goes up to the water surface only when we get too strong light. Okay, so that was in the conjunction scenario, the only possible combination that gives us, a 1 as the output. So it just propels itself upward, okay, looking for food. And if it's, I don't know, not hungry or whatever, it either drifts idly by or moves sideways, right? So it either propels itself or not, and let current basically take it as part of like a random exploration process. So in this case, we have wide proximal inputs, but wide distal outputs. Okay, so it's not just the immediate environment, but it's actually the distal output, namely seeking food at the water surface. Okay, and a similar story can be told about what happens when the plankton actually computes OR. Okay, so when we compute OR, we have more combination of inputs, right, that give us 1 as the output, is what gives us like the function we want. Okay, so we might say that when the plankton is an environment that's very rich with other conspecifics, okay, we might say that if some light is received, whether it's little light or strong light or whatever, but we group them together, the plankton moves either sideways, doesn't matter left or right, or upward to basically distance itself from other conspecifics that compete for the same resources, whatever they are. So the idea is to say that whether the visual motor system in the plankton computes and the NOR, that basically depends on the wide proximal function of that subsystem, okay? And that might be either distal input, distal output, or combination of both, right? So in the example I showed you, the inputs are proximal, the output is actually distal. It can also be the other way around. And then, this is basically the adaptive value. So either we get food or we avoid competition with the conspecifics. So just as a disclaimer, because we want to give eventually a teleological function as part of the individuating contributor, what we focus on is functions rather than just mere effects. Okay, simply things that occur maybe accidentally. And the reason it's important for us, obviously, is because we also want to be able to account for miscomputation, right? And on this account, or when we take something like selected effects theory, we might just say that the system miscomputes when it's not actually performing the function it's selected for it has been selected to do. Okay, so with that picture in mind, what do we get from this story about functional individuation, and how does it pertain to the indeterminacy of computation? So here's a clue. You might remember it from a lecture we saw eons ago. So we've got Jack probes. Okay, so option 1, we might say, and this is basically just a way to make the point clearer. This is the same visual motor system that we thought before. We just explained as something that contributes to the behavior of the plankton, and we didn't talk about any other downstream consumers. But to make the issue more, I don't know, plausible or easy to grasp, let's assume that the visual motor does what it does by connecting with some downstream consumer 1. And remember, this visual motor system is basically indeterminate between conjunction and disjunction. So here, let's assume that we have Jack probe 1 connected to this system, and then at least one of the input lines of this downstream consumer basically gets an input from this probe 1. Okay, so this basically means I'm now choosing the grouping whereby no light and little light were grouped together and the strong light was separate. Okay, So we can think about this probe as a separate entity, but we can also think about this probe as being implemented here already in the downstream consumer. I think it doesn't matter much. In this case, we say that the visual motor system computes conjunction. And then same story. Now the grouping is different, low separately and not low, no light and little light and strong light grouped together. Then we connect it to the probe, the second probe and downstream consumer, and we get this junction. Now, the other point to consider is the fact that, as I think Jack also mentioned yesterday, there's no reason why we cannot connect various probes simultaneously to the same visual motor system, right? So in this case, let's just assume, because we're dealing with two functions, we have two probes connected, okay? And then one probe is connected to this downstream consumer, other probe is connected to this downstream consumer, and then in this case, we might even say it's computing both mathematical functions at the same time, okay? I'll say what the implications of this picture are in a second. So if we accept this picture about indeterminacy and functional individuation, if we think that the indeterminacy problem is actually a problem, it's dissolved, okay? If I don't want to call it dissolved, Jack, and I want to call it something else, I'm open to interpretations as well. So we might say that the visual motor system may support two computations simultaneously, right? And this is basically following I guess the main gist of what Dimitri is saying. We might say that this is done due to its physical properties, namely responding to light and doing something that results in the relevant behavior in the environment. So the physical properties, we simply appropriate degrees of freedom, right? Like we saw the gate that Oron describes. The appropriate degrees of freedom is what gives it the ability to compute and or XOR, or maybe and XOR together. Okay, and on this, the state transitions actually depend right on those degrees of freedom. So far, so good. And now we want to say two extra things. First of all, if we talk about the visual motor system, because I said that I want teleology to play a key factor in the individuation here. So we would say that the visual motor has the function to compute conjunction or disjunction, right? It doesn't matter. Simply if it has the right evolutionary history, right? That depends on the downstream consumer it's worked with. So say that in the evolutionary history, we had the visual motor system with the same, physical properties that it has, and say that only downstream consumer one was connected, right? And serves the function and the benefits and whatnot, then we would say that the visual motor system has the function to compute conjunction in this case, say if it was consumer one. And we would say that the visual motor system works as, okay, something that happens in actual fact, in actual point in time. Okay, so it works as an AND gate or as an OR gate, okay? And then it computes conjunction or disjunction respectively. If at that particular time, it's the right, and it's the right context, right? Either the first or the second downstream consumer. So if it's the first, it's conjunction. If it's the second, it's disjunction. And then that allows it to successfully perform this teleological function. And by this teleological function, I mean what it does in the environment that serves its purpose. And this is where the multiple computation comes into play. It might also work as an AND gate and as an OR gate simultaneously at the same time, if both consumers are basically connected and using the probes and whatnot to tap off both possible computations, right? So it might be the case that it has the function to compute and OR, depending on the evolutionary history. At present time, saying that it's only connected to downstream consumer one and only that is serving some purpose for the organism, say looking for food, then it works as an AND gate, okay? But it certainly may be the case that both downstream consumers are connected and they're both exploiting this function right now, then we might say that it works as both gates. It doesn't really work, this thing, when we have the and and or in the context that I described, right? Because in the end scenario, only when you reach this the surface of the water can you get food, and in the case of the or, even if you move sideways, you're actually escaping conspecifics. But again, in this case, we might actually think of a different example like the or and XOR that Oron showed yesterday. So if that's true, then a physical computing system doesn't always have a single computational identity. So we may not be able to say always in every single context, this only computes this particular mathematical function. It may compute several. 5. Great, I can even have coffee in this time. So the contextual corollary of this view is the fact that the teleological functions of this particular visual motor systems and others to compute conjunction and disjunction are dependent on either recent or long evolutionary history, okay, that basically shaped the particular system. This goes back to stuff that Lotem said as well. To maximize the adaptive benefits, okay, in this case, the plankton or something else, by virtue of exploiting the computations that it performs in the environment. One implication of this wasn't planned originally, but I think it's unavoidable, that computation becomes contextual, right? So there's no actual computation in itself when we're talking about physical computation outside a particular functional context. It actually raises interesting questions about artificial systems as well, but I'm more interested in biological systems, at least for now. This I'm going to do very, very quick because I said that I don't need to appeal to semantic content. So the question is whether wide function is actually equivalent to representation. If so, then we collapse into the semantic view and we are trying to avoid it. So I think there are like basically 3 possible options for computational individuation to work by appealing to either function and representation. It's and or in this case. So one option with the toy example that we have in mind is to say that plankton simply don't represent. Okay, there's no representation involved. If that's true, then we can still individuate the computations that are performed by the plankton. Then we simply don't need semantic content, and we are able to individuate the computational states or processes. Another option is basically to say, sure, plankton do represent in a very limited sense because it's a very limited or basic organism. But then we say, all we need to appeal to is to the wide distal function. Okay? So in this case, we had, remember, proximal input, but distal output. So the behavior in the environment. And that basically is sufficient for computational individuation. We don't need to talk about representing anything. And at least according to teleosemantic theories, representation also requires some other conditions. So it's not just the function. Some say it's a constancy mechanism, some say it's robustness, and there are other options on the table. If you want, I can get to that in the Q&A. And of course, the last option is to say plankton do represent, and the semantic content is needed for the computational individuation. And we know at least one person that advocates this view. And with that in mind, so when narrow individuation is insufficient for determining the computational identity of the system, we argue that wide distal functions can actually do the job, right? So and that means determining the narrow proximal functions, right? Remember, like what the amygdala does or what the visual motor system does. And then doing that without invoking semantic content. And if that's also right, then the indeterminacy of computation problem, phenomenon, whatever, dissolves, okay? We just say that we accept that physical system S may simultaneously compute multiple mathematical functions, concurrently. This has some implications for what Mayor and Orly were telling us about the computational theory of mind, but we can talk about it in the Q&A. Done. Diane, you can see us, hear us, and no screen sharing, so happy? Good, excellent.
Oran?
Yeah, you were on.
Yeah, Oran.
Well, let's assume that the plankton has these two consumers, all right?
Mhm.
And what the function of one was seeking food, the other was, I don't remember, going up.
Mhm.
Doesn't matter. Let's say that one consumer was developed evolutionary in the
Evolutionary history, yeah.
of and then the other consumer arrived the plankton one day, traveled, and somehow the second consumer was added to it, like swampland, something like this. So now, according to you, so you have now two identical planktons, right?
Mhm.
One plankton, the second consumer was developed through history, in the other case not. So you will say, in one case we have computation, in the other case, no, right?
In short, yes.
Okay.
A longer answer would say, this is basically the standard semantic or teleological response, right? So if you want to rely on long evolutionary history, then certainly it's out of the question. If, however, we accept something more liberal, like the account that Justin Garson advocates for, right? So we don't just talk about long, million year period in terms of the evolutionary history, and you also allow for, like, I don't know, trial and error learning or whatever, synaptic pruning, if we want to talk about synapses in the brain and whatnot, then that can also acquire function given a sufficient period of time. So the first time that it happens, like as soon as the downstream consumer is connected and results in some effect, like, I don't know, so suppose the thing was doing just sick food behavior at the surface of the water, okay, and this was the evolutionary function, that's fine. And let's suppose that this downstream consumer has like this accidental effect leading to dispersing from conspecifics, okay? So we would say, at least for some time, we would say it's still not the function of that particular context, right? The visual motor system plus the downstream. It does not compute or, at least for a certain period of time.
It does or and maximizes its adaptive whatever. And
yes, but remember, that's always relative to a certain period of time. It's always averaged, and it's not enough. Like, it might be the case that I pick a particular apple, and I don't know, maybe it's it has some nutritious value, and I eat it for the first time, and it gives me some adaptive value. But overall, over evolutionary time, it has small amounts of poison. So the more I eat it, the more I'm disadvantaged in the end. So it's not clear that we want to say from day one it has an evolutionary or adaptive value. Mark, do you want to add anything on that, or should we move on to the next question?
We can move to the next question. Can you hear me?
No, we can't. Yes, we can.
Oh.
Very Wait.
Sorry.
So you're okay with the swamp man?
Yeah. So my connection is not great, so I'm sorry if I miss some bits. Sorry, but I think the answer you gave is perfect. Thank you.
Okay, great. If he's okay with that, I'm okay with that.
Related. So, first of all, I think it's a really interesting example. I'm wondering, let's say both functions are adaptive.
Mhm.
So
they've been, you mean adaptive in the sense of what we said about the long evolutionary history? So they've been, okay, cool.
And it's like, you gave examples of the functions that make sense, so then what would you say? is a-
About what? About the visual motor system?
What does the function?
It computes both. It computes both functions. And it subserves two different biological functions. So one function would be to search for food, and then, you know, one downstream consumer does it, and then for the disjunction, another consumer, you know, is responsible for that, and then it disperses from the conspecifics. However, as I said before, because my example here was and then or, you cannot have a successful performance of the function simultaneously when it's and then or. It might be possible when we consider, I don't know, and then SOR, or and then I don't know, whatever, something else, implication relation, whatever. And then it might be the case that you can perform one function and get an adaptive value, and another downstream consumer uses the very same output of the visual motor system to do something else. Okay, so think about, you know, I don't know, the dopamine system. Okay, it might have different functions, and they might be serving different functions at the same time, right? So your question is relevant when you're asking about the two functions performing what they perform, like those downstream consumers at the same tx time. So at the given time, both of them are working, right?
Yes, I mean, if it's defined by etiology, then they're always doing the same function at the same time.
So that's why we separate two descriptions of what the system does. We would say that the visual motor system has the two functions, conjunction and disjunction, even if you cut off, if you do like lesion studies or whatever, and you decide, I don't want these downstream consumers connected anymore, you can disconnect them. Due to the evolutionary history, we would still say, if Mark agrees, that the visual motor system has the functions to compute conjunction and disjunction. And then in a particular time, T1, only one consumer is actually exploiting it, then I would say the visual motor system has the two functions to compute and or, but in this particular time, in this particular context, when it looks for food, the downstream consumer one is basically exploiting the function, okay, and then it computes conjunction. So it's like the distinction between having the function. So it's like the heart has the function to pump blood, even if it stops pumping blood at a particular time because the surgeon disconnected the vessels, or I don't know, injected it with some material. We would still say that the heart has the function to pump blood. It just doesn't pump blood at this particular time. So this is basically the equivalent. Mark, you want to correct me if I was totally wrong? If not totally wrong, it's okay. Okay, it doesn't hear me. Okay.
He said no.
Fine.
Yeah, it's great, Nir. Sorry, I'm just saying it's great.
Excellent. Who was next?
Dimitri.
Yeah, thanks, Nir, for that a lot. I mean, I totally agree with the view, and I think it's
Just stop here.
right. No, I mean, that's it. I'm only going to say positive things in what follows. So I had one question and one suggestion / comment. So the question is, why were you so cautious in the conclusion? Because in the conclusion you say that, well, when narrow individuation, functional individuation is not enough, then we have this. Why not just go and say, well, it is always wide functional individuation, right? So why have it as a source of, further case, just that, tool that we may use when the first one didn't work, rather than, well, this is the accounts, right? And that's how it should be. And the comment / suggestion is, I mean, I mentioned to you already yesterday over dinner, right? The whole discussion in cognitive ontology about neural reuse, right? And there is this this distinction that people like Anderson and Bergeron have made between computational workings and computational functions, where they think that the computational workings remain the same, but they can be exploited for different functions, right? So that the same sort of neural resources can have different teleological functions and so on and so forth. While you seem to be going beyond that and saying, well, even the workings, right, the computational workings may vary with context, right? And I think this is, you know, a very interesting addition to that particular debate in cognitive ontology. So I think, you know, over and beyond the problem of indeterminacy of computation, I think this is also quite interesting and useful for this other literature on, you know, computational contextualism and so on in cognitive ontology. So I think it would be very nice to go also in that direction. And yeah, and finally, in connecting to this, so it seems that the account does solve the indeterminacy of computation, right? It does lead to, in some cases at least, multiplicity of computations, but not in a way that leads to those sorts of metaphysical problems with multiple minds and stuff like that, right? Because it may well be that you know, different downstream consumers, it's an empirical question, and one that, you know, it can be investigated, that indeed different computations are being, or, you know, different degrees of freedom of the same kind of vehicles are being exploited by different downstream consumers, right? Such that overall the system, there are two functional systems computing different things, even though the vehicle is the same, right? And that doesn't seem to be a metaphysical problem, right? It's just an empirical question whether this actually happens in brains or not. So it also seems that, you know, you end up, and this is a good thing, distinguishing the multiplicity of computations issue, if it is an issue at all, from the more metaphysical problem of, you know, the indeterminacy of computation, right? So I think it helps also with that.
Well, first of all, Ari, I think we should stop with the questions right now. Okay? So thank you for that, Dimitri. Mark, I hope you're taking notes. So for the two comments, I think absolutely we have to add it to the to-do list in the ever-growing paper. It started with like 5 sections. I think we have now 20. So thanks for that. For the more cautious conclusion about, you know, narrow versus wide and whatnot, why not appeal to wide distal always? I think the simple, honest answer is that sometimes you simply can individuate simply by looking at, you know, the narrow properties, and, you know, there's maybe even no danger of indeterminacy, for example, right? I mean, indeterminacy doesn't arise always in every case. There are cases where the indeterminacy arise, but where, you know, narrow individuation is sufficient, we see no reason to appeal to those other factors when you can do it in a more, I don't know, economical way or something like that. But, you know, you'll probably need to speak about specific examples in order to support it better. But again, thanks. So, and here's
yeah, I guess I'm just not. I haven't got the big picture in focus yet. So tell me where I'm wrong.
Here.
As you started, you know, through about halfway through the paper, I thought, you know, the story was going to be that the way to fix what computation is happening is to look at the goings on in the pond. But then you kind of switch tack when you introduce the probes. Now, before you introduce the probes, the question was going to be, well, what mechanism is it that determines which of the behaviors that happen? You know, is it this one or that one, or maybe both of them? But what mechanism underlies that fact? Your answer is the probes. But once you've got the probes, you don't really need to look at the goings on in the pond to fix the computation. You just look at the outputs of the probes, or the single probe.
I'm not sure I can see how just by examining the probe I can get the actual function. What we say is, in order to individuate the relevant computation, we sometimes do have to look outside the boundaries of the system. So the original toy example started simply by appealing to the visual motor system and behaviors outside, and not talking about anything in between. Supposedly the visual motor system gets the input and is connected directly to the, I don't know, the propelling system of the plankton or whatever, okay? So in that case, we have the visual motor system, it gets inputs, it spits out outputs, and basically in order to see what it does, it's not enough to just look at, the propelling system itself, because it's like and or, the behavior in the environment, like the actual swimming patterns and whatever would be the same. And this is where we have to appeal to the distal function, distal output in this case, and see whether it's actually rising to the surface of the water because it wants food, or it basically either drifts idly or swims or goes upward, etc., to disperse from conspecific. So that was the point that we make in order to show that narrow individuation will not do the trick in this case, probe or no probe. When I talk about the consumers, that's more to support the idea of separating the distinction that I also alluded in responding to Lotem, saying that the same visual motor system might have multiple functions. It might have the function to compute conjunction, it might have the function to compute disjunction, maybe other functions as well, right? In a more elaborated gate. But then the idea of the probe is basically to say, look, now you have these downstream consumers, okay? What we're doing is actually doing, in your terminology, Oroning, okay? So it's basically about the grouping of the different physical states. And because the physical properties are, the same, as Meir keeps reminding us, so the physical structure remains the same. And what we do with the probe is basically just utilizing your machinery to basically look, we can actually mechanize the whole process. It's not like we need an observer from the outside to say, this one picks this output, this one picks that output. We basically say the downstream consumer one looks at the grouping or exploits the grouping in a way that results in conjunction. Consumer two basically exploits at the same time the grouping, the other grouping, so the medium and higher together, and that results in ORing or disjunction. And then when you look at what the overall system does, then in one case, downstream consumer one, it seeks food, downstream consumer two, it disperses from conspecifics.
Yes, this may simply turn on which sense of function we're using, like truth function or some other sense of function. I certainly agree that it's that the probe is the mechanism that kind of underlies which behavior is going to be evinced. But I still don't get the why you need the goings on in the pond as part of your account of what fixes the computation once you've got the probe in place, because in a sense the probe is just spitting out truth values, canonical pulses of some sort, or whatever the underlying medium is. So you want to know whether it's doing angle or check out the outputs of the probe. You don't need to look at it all.
Well, again, our functional individuation does appeal to philological function in an etiological sense. So we actually refer to the history of the system. So it might be the case that the visual motor system now is not connected to any downstream consumers at all. We still want to say that it has those two functions, okay? And in a particular time, it might be the downstream consumer one is connected, okay? And then, I don't know, it uses the probe. Maybe I didn't understand the notion of probe very well, but the idea is that probe plus the downstream consumer makes it the case that it utilizes one particular grouping and not the other, okay? So I did get it right, okay, good. And so then that gate supports a particular behavior in the environment. Even when you have both, okay, you can't always tell, and that's I guess the moral of the story, you can't always tell whether it's computing conjunction or disjunction, say at a particular time, simply by looking at the internal workings, right? I think in this case, we don't even need to appeal to the idea of a probe, essentially. You can just say, okay, you have the downstream consumer and the downstream consumer does this. And so this is the function is computing. But this goes back to what Oron was saying before about the swamp plankton, right? So we now have the swamp consumer too, that's connected. Maybe it's doing something, maybe it's not exploiting by mere accident, I would say. It's using the grouping that results in disjunction. We don't want to say at that point still that it has the function to compute disjunction or that it actually computes disjunction simply because it is the case that downstream consumer 2 takes the OR function and then does something with it in the environment. At that point, we would say it still doesn't have the function to compute or. This depends on the evolutionary history or some more recent history of the organism.
Okay.
But we will talk more for sure.
Well, we're officially out of time.
Oh, we are?
Yeah, it's 15 now.
Okay,
Yeah,
so
we have to finish because the driver, if we want to go.
you don't have to convince me. I'm okay to finish.
We have to be there in 5 minutes.
Okay.
All right.
No worries.
Let's
Thank
end.
you.